Here we have another example. So, suitcase thrown along the floor. It has a speed of 1.2 meters per second. So I'm going to draw a rough sketch over here to the side. Our suitcase initially has a speed of 1.2 meters per second. It slides 2.2 meters before coming to rest. Now this problem would be easy enough to use net force equals ma in kinematic equations. But we're looking and learning another approach to solving motion, so that's why we are asked specifically to use work and energy to find the coefficient of friction on the floor. So again, work, kinetic energy theorem. We can relate forces to the change in kinetic energy, which means we can relate force to speed by this equation, our work kinetic energy theorem. So final kinetic energy, 1/2 mv final squared. Initial kinetic energy, 1/2 mv initial squared. We know the mass of this suitcase is 15 kilograms. We know V initial is this 1.2 meters per second. We know V final is 0. It's coming to rest, so there is no final kinetic energy. And then this total distance it slides is 2.2 meters. All right, so net work. The work done by all of the forces. I'm going to just draw my free body diagram at this initial moment in time. I'm not doing a good job of drawing the vectors in any sort of comparative way. We do know, since the floor is horizontal, the normal force will need to equal mg. Neither the normal force nor gravity will be doing any work. So the work done by the normal force is 0. The work done by gravity is 0. And that's because work is force dotted with displacement. We don't have to integrate because these forces are constant. The dot product means we only care about the components of the force that are parallel with the displacement. We could write this out generically as the force times delta S times the cosine of theta. For the normal force and for the force of gravity, the angle between the forces and the displacement, which is horizontal, is 90 degrees. Cosine of 90 is 0. So again, the dot product is multiplying components of the force parallel to the displacement. So it turns out is only the friction force that is doing work. And because the final kinetic energy is 0, we get 0 minus the 1/2 mv initial squared. So the work done by friction, using this equation to the right here, will be the force of kinetic friction times the distance it acts over times the cosine of the angle between the force and the displacement. So the displacement, this baggage is sliding to the right, while friction is acting to the left. So the angle between these two is 180 degrees. Well, cosine of 180 is -1. So we get and find that the work done by the force of friction is negative, which should make sense. Negative work means energy is being removed from the system, which is why the baggage is slowing down. So these negative signs are actually going to cancel on both sides. From here, we do want to plug in the force of friction. The force of friction, its value depends upon the coefficient. I guess I shouldn't skip that step. Coefficient of friction times the normal force. But again, the coefficient of friction times the normal force is going to be mu times mg. The normal force needs to equal the force of gravity because the baggage is not accelerating vertically at all. So plugging that in for friction, common mistake is to forget the delta S. So we do need the force of friction multiplied by how far this suitcase slid. Finishing up my equation, it turns out the mass of the suitcase is not going to matter in this case. You might be able to think back to when we've done a problem in the previous section with Newton's laws, where if it was moving horizontally and just friction, the mass sometimes canceled. Well, we're seeing that again in this case. So we're looking for this coefficient of friction. I'm going to bring the G over and the delta S over. So V initial 1.2, that needs to be squared. G is 9.8, delta S is 2.2 meters. Plugging that in. Getting a very small value. Now we should end up with no units. Let's make sure that is the case. The speed is in meters per second, which has to be squared. G is meters per second squared. Delta S is meters. So we have meters squared on the top and the bottom, second squared, top and bottom. So we do end up with no units. If you look at this and go back and compare to a similar problem in the previous section, you will find that this is the same equation that we would come to even if we said net force equals ma, found A, plugged it in a kinematic equation, and solved for mu. So ultimately, we're just looking at another way to solve problems. When all said and done, it doesn't matter how we approach a problem, but for this section specifically, I'm going to require you to use equations from this section, even though net force equals mass times acceleration would still technically work. So make sure you're practicing these specific concepts.